Works.
It works, yeah. Thank you. Yeah, thank you for the introduction. As you heard, my name is Dominik, and today I present co-work with Emanuel, who is also sitting over there. And yeah, we both jointly lead the social computing research area at the NOS Center in Graz, Austria. And the NOS Center is an applied research center on trustworthy AI. And in this work, we research popularity bias in collaborative filtering-based recommender systems. Good, so I think we can all agree that in general, collaborative filtering is among the most well-known methods for recommender systems. And this is also the case for recommending multimedia items. And this could, for example, be movies, music items like songs, digital books, or animes, for example. But what you probably also know is that collaborative filtering is also prone to popularity bias, which means that unpopular items are underrepresented in the generated recommendation lists. And in recent research, it was also shown that this popularity bias of collaborative filtering also affects the users who are interested in popular items, so that they are treated in an unfair way, you could say. And this was especially researched in the domains of movies and music. And in this work, we now expand these studies, so not only looking on movies and music, but also other domains like digital books and animes in our case. And yeah, we evaluate all these domains with a common evaluation protocol in order to study popularity bias on two levels and to address two research questions. So the first one on the item level. So if there is a relationship in all of these domains between the popularity of the items and the probability that they will be recommended by collaborative filtering. And the second one, more on the user level. So if this also affects the recommendation quality that users get with less inclination to popular items. Okay, now starting with the data sets we used. So as I said, we have 4 different domains, and we have 4 data sets that represent these domains. And for music, we use Last.fm, and here the LFM1B dataset, which was provided by the Johannes Kepler University in Linz. For movies, we have MovieLens, the well-known MovieLens 1M dataset provided by GroupLens. For BookCrossing, so for the book domain, there is a dataset by the University of Freiburg in Germany. And for anime, we have the MyAnimeList system with a dataset which was provided by a Kaggle challenge. And yeah, more infos on all these datasets can be found in the paper. But in general, we removed all users with less than 50 ratings and more than 2,000 ratings. And in all these datasets, we created different user groups. So we have the low popularity user group, this LowPop group, which are the 1,000 users with the lowest inclination to popularity. Then we have the high popularity group, which are the 1,000 users with the highest inclination towards popularity. And we have the medium popularity group, so this MedPop group with medium inclination, so just in between. And yeah, all these data sets along with the user groups can also be found on Zenodo. And in this table, you also see some basic statistics just to illustrate that we're dealing with different data set sizes, different kinds of sparsity, and also different ratings or preference ranges there. Okay, yeah, before going into the results, we need some more formal definitions of popularity. So on the item level and on the user level. And on the item level, we can define the popularity of an item as the fraction of users who have rated this item. And based on this, we can also define the average item popularity in the user profile, which is the average popularity of all items the user has rated in the past. And we can also say that an item is popular if it falls within the top 20% of popularity scores of the items. Then on the user level, we can do similar things. So we can define the set of popular items in the user profile. So how many items the user has rated are popular, and the ratio of popular items in the user profile. And we use this ratio of popular items in the user profile to create these different user groups I told you before. So this LowPop, MedPop, and HighPop user group. And we do this in cases of MovieLens, BookCrossing and MyAnimeList. And in case of the music domain, we use a bit more sophisticated metric called the mainstreaminess score, which was also defined by the Johannes Kepler University in Linz. And this is especially designed for the music domain, where we have repeated consumption patterns, because they're usually you listen to the same artist for a lot of times. And this mainstreaminess score is just defined as the comparison between the artist playlist count distribution of a given user compared with the artist playlist count distribution of the average user in the system. So the aggregated distribution of all users, you could say. And if this mainstreaminess score is high, then we have a mainstream user, so high inclination towards popularity. And if it's low, we have a low mainstream user, you could say, so low inclination towards popularity. And to get a better feeling of this scores, in this plot, you see the average item popularity in the user profile plotted over the user profile size. And what's interesting here is that we have a negative correlation here. So this means that the higher the user profile size, the lower is the average item popularity in the user profiles. And this is especially true for the low popularity group. So we see them here plotted with these green dots, which, based on this, we could conclude that low popularity users are the users which have the largest profile size, or in general, large profile sizes, and therefore should also be important for the recommender system, because they provide quite a lot of data, and so they should also be treated in a fair way, you could say. And in order to test this, if this is really the case, we use a common evaluation protocol for all these domains and data sets. So we use the surprise framework, which is a Python-based framework. And there, the recommendation task is formulated as a rating prediction task. And in case of Last.fm, we do not have the specific ratings, but we have this artist play counts. And so we try to predict them there. And we use the mean average error metric. This means the lower this metric, the better. And we have 4 different algorithms that we test. So we have 2 k-nearest neighbor-based approaches, 1 matrix factorization-based approach, which is non-negative matrix factorization, and 1 co-clustering-based approach. And we use a random 80-20 train test split with 5-fold cross-validation. And to test for statistical significance, we use a pairwise t-test between the different user groups. So because we're interested in the low popularity user groups, this means then tests between LowPop and MedPop, as well as LowPop and HighPop. Yeah, and again, all these algorithms and the protocol is available as source code on GitHub, and of course works with the dataset that are provided via Scenario. Okay, so now starting with the popularity bias on the item level. In these plots, we see the recommendation frequency on the y-axis plotted over the item popularity for the 4 algorithms and the 4 data sets, which means we have 16 plots here. And in all these cases, we see that there is a positive relationship. So the higher the item popularity, the higher is also the probability that the item will be recommended. And here to see more details, I zoom in here on 4 specific cases. So matrix factorization, co-clustering on Last.fm and MovieLens. And of course, again, we see here this positive relationship between these 2 variables. But here we also see the different user groups. And what's interesting is that this relationship is the weakest one for the low popularity group. And now to see how this affects the recommendation quality on the user level, in this table, we see the mean absolute error scores. Again, for the 4 data sets and the 4 algorithms, but here we also see it on the group level. And what's interesting is that in all cases, the low popularity group gets the highest prediction error, which means they get the worst recommendations, which is also statistically significant compared to the other 2 user groups. And when looking at the different algorithms, this is indicated here in bold, we also see that different algorithms provides best results in different data sets. So for example, for books and for animes, the k-nearest neighbor-based methods provides the best results. For Last.fm, it's matrix factorization, and for MovieLens, it's the clustering-based approach. And when looking at the different user groups, which is shown here then in italics, the best results, we see that not always the high popularity group provides the best results, which is interesting. So for example, in Last.fm, it's the medium popularity group which gets the best results. And this already brings me then to the conclusion and points for future work. So we have investigated popularity bias here on two levels, the item level and the user level, where we found that popular items have higher probability of being recommended. And on the user level is that this low popularity group receives the worst recommendations. And this is quite unfortunate because we have also shown that this low popularity group have the largest user profile sizes in these four systems, which also means that they should be important for the recommender system, if you think of them maybe as some kind of data provider. And yeah, therefore should also be treated in a fair way. And for future work, we want to look at some of these differences we found in the results. So across the different user groups and the algorithms. So for example, an interesting question is, why does this medium popularity group gets the best results in Last.fm? Because if you just think on popularity bias, it should be the high popularity group. So this is one question we want to investigate. And of course, also look in different popularity bias mitigation methods. So there are some methods, for example, based on calibration, based on personalized re-ranking, on aggregate diversity, but also some in-processing methods based on regularization. And there's, for example, one nice work which was published by our workshop organizers. And this we would like to try out then on these data sets. And of course, there are, for the evaluation perspective, there are also some more metrics how we can evaluate popularity bias. For example, by the group of Robin Berg, this group average popularity score, which we could also then use for our different user groups. Okay, yeah, then I want to thank you. On this slide, you again have the links for the data set, for the source code, also for the paper. And I also want to point you to some posters we have on Wednesday in the main track, and also on Thursday in the industry track, which are also about recommender systems and popularity bias to some extent. Thank you very much.